Professor R. Asokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former Professor and Head of the Department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series for the BSc Honours Physics students, and we have been going through a series of lectures on geometrical optics, and this is the lecture number 7. This lecture we will be mainly seeing the graphical construction of the image using cardinal points and also about thick lenses. So, the contents of this lecture are as follows: need for cardinal points, nodal points and nodal planes, construction of image using cardinal points, thick lenses. So far we have been talking about the thin lenses. In today's lecture we will have something about thick lenses also. You all know what is meant by a thin lens. A thin lens is one for which U and V are much larger, or in other words the thickness of the lens will be very small. That is the reason why it is called thin lens. And for the case of thin lenses, we consider a coaxial system. We do not consider a single thin lens. In any optical instrument, as all of you know, you have got an objective and you have got an eyepiece in a microscope and in a telescope, and by now you know in optical instruments you have a set of lenses, a coaxial lens system. When you have a coaxial lens system, we have obtained formally for the focal length, or the main objective is where we will be getting the image. For a object that stands on the principal axis, where will we be getting the final image, and we saw the sign convention and other approximation that we have used, or we consider all the rays to be paraxial rays, as I told you in the earlier lectures also. Because you consider paraxial rays, the angle subtended by the rays on the surfaces of the lenses will be small, in which case you are permitted to have tan alpha to be replaced by alpha, and also sin theta can be replaced by theta, because theta is small or alpha is small. We have been primarily assuming that the rays of light which are incident on the surface of the lens are paraxial rays, and then only we can make the approximation that I mentioned just now. In the earlier lecture, we saw them all the 6 cardinal points, and now in this lecture we will be talking about the nodal points and nodal planes through which the light ray will pass through. So, nodal points are points on the principal axis where light rays are not getting refracted. The light rays pass without refraction after intersecting the optic axis. In a thin lens, the nodal point is the center of the lens, because the lens is so thin, the nodal point is at the center of the lens. The center separates into two nodal points. The planes passing through the nodal points and perpendicular to the principal axis are the nodal planes. So, you got two nodal points, as you will be seeing now, and the nodal points will be on the principal axis, and the planes which pass through the nodal points are the nodal planes. Something like the principal planes we saw in the last lecture, where the planes are passing through the principal points. Now, we are talking about planes which are passing through the nodal points. As I told you, the light ray does not undergo refraction when the light rays are incident on the nodal points. Nodal points are points on the principal axis, where light rays without refraction intersect the optic axis. Mainly, the thing that should be remembered are these points about which we are talking were proposed by Gauss for simplifying the problem. What is the problem? You have got a pair of lenses. You have got an objective lens, then you have got a eye lens, and for every lens when the light ray is passing, there will be two refracting surfaces. So, for the first lens there will be two refracting surfaces. The light ray is incident and undergoes refraction. It goes through the lens, and again when it comes through this surface, it goes from the medium, namely glass, to air. So, air to glass and then glass to air. For every lens, the light ray will undergo two successive refraction. For a pair of lenses, there will be four refracting surfaces. Now, in order to do away with the cumbersome refraction processes occurring at the four refracting surfaces, Gauss introduced the cardinal points and introduced the hypothetical planes, which are called as principal planes and nodal planes. So, the principal planes and nodal planes are hypothetical planes which are responsible for simplifying the problem. Otherwise, you have to do the cumbersome process, namely looking at the refraction at the four surfaces corresponding to the two lenses. That is being done away with the planes that were introduced by Gauss, namely principal planes and the nodal planes. And so, you have got a nodal plane here. A nodal plane should be a plane passing through the nodal point. You have got N1 and N2 are the nodal points. We have already seen H1, P1 is the one of the principal planes, P1 is the principal point, and P2 is another principal point. H2, P2 is the second principal plane, whereas H1, P1 is the first principal plane, and N1 is the nodal point, N2 is the nodal point. The angles subtended by the rays at N1 are alpha 1 and alpha 2. Remember, the light ray does not undergo any deviation. The light ray is coming from A, incident at N1, and so the light ray which is falling at T1 goes to T2, and you got the ray going from alpha 2, the angle is alpha 2, T2 to R. So, this is the point where the light ray goes, and remember, the light ray does not undergo any refraction while passing through the nodal points. So, AN1 is a ray of light directed towards the nodal point N1. After refraction through the optical system along N1, N2, light emerges out from the second nodal point N2 in the direction N2R parallel to the incident ray. Remember, N2R will be parallel to this one, that is AN1, and so N2R is parallel to H2 F2 and also parallel to AN1. That is what I am. So, the light emerges out through from the second nodal point N2 in the direction N2R parallel to the incident ray. So, N2R is so this is the incident ray. So, the incident ray, and so these two will be parallel. Therefore, the points N1 and N2 are a pair of conjugate points on the axis having unit positive angular magnification. The distance between two nodal points is always equal to the distance between two principal points, and so the distance separating the two principal points and two nodal points are one and the same. So, P1, P2 should also be equal to N1, N2. This is P1, P2, right? P1, P2 should be equal to N1, N2. That is what I mean by saying that the distances should be equal. And so, with this we come to the end of what we have to discuss with regard to the thin lenses. And now, let us see, using these points, the principal points and the nodal points, how you can obtain the image for a pair of lenses. You got a two lens system, how the two lenses are replaced by the the H1 P1, that is the first principal plane, H2 P2 the second principal plane, and N1 N2 are the, what are N1 N2? They are the nodal points. And so, for an object that you have got A B, you have got an object here A B, which is on the principal axis. How to obtain the image? You have got A1 B1 is obviously the image. How the image is obtained from the object? That is, in other words, the construction of the image using cardinal points. Now, we are not going to discuss about the refraction that will otherwise be taking place when you have got a lens L1 and another lens L2. So, instead of looking at the refractions taking place at the two surfaces for the lens L1 and similarly the other two surfaces for the L2, these lenses are replaced by the so called principal planes and the cardinal planes, or in other words the cardinal points. Using the cardinal points, how we can obtain the image. So, the construction of the image using cardinal points. Let us look at the F1, F2 and all these things, that the quantity that mentioned here, X1, F1, F2 and all. So, F1, F2 are the principal foci. You find F1 here, F2 here, they are the principal foci, and P1, P2 are the principal points. By now, you should be having clear idea about P1 and P2, they are the principal points. And now, obviously, N1 and N2 are the nodal points, they are the nodal points. AB is a linear image, which is an object placed on the axis. You have got the object placed on the axis, this is the AB, right? AB is the object. Now, what is the problem? Our problem is to obtain the image. So, the problem is to find for the object AB, where is the image? To start with, for the point A, where is the image? For the point A that you have got here, the light rays are incident along A H1, another light ray is incident and it is passing through A N1, another light ray from A goes along this direction A K1, is that right? So, we will be talking about three light rays, A H1, then A T1 passing through the nodal point N1, and then a light ray which is passing through the first principal focus F1 to K1. So, A F1 K1. Now, we will be considering the different rays which are travelling from the point E. That is what we will be doing, and therefore, the problem is to find the image point for the object point E. For the object point E, the image is point, corresponding point is A1. Okay. So, this is the problem before us. We make the following construction. So, this diagram is of considerable significance, because it replaces the lenses by the nodal planes and the principal planes. The lenses are replaced by the hypothetical, or they are hypothetical planes, right. For sake of convenience, they are introduced. So, a ray AH1 is drawn parallel to the axis touching the first principal plane at H1. So, where is AH1? So, AH1 is the light ray coming from the point A of the object, is the object space, this is the so called object space, this is the image space. So, from the object space, from the point A, light ray is coming to AH1, H1 is what? It is a point in the principal plane, P1 is the principal point, AH1, H1 P1 is the principal plane, H1 is a point in the principal plane, right. So, a ray AH1 is drawn parallel to the axis touching the first principal plane at H1. We will go through the remaining things with regard to the light rays which are passing through them from the point A to obtain the image at the image point A1 after the break. Welcome back after the break. Now, what we have been trying to obtain is the following, namely the graphical construction of the image, how to obtain the image for a given object. You got getting a inverted image, right? You got getting a inverted image. You see here A1, B1, the inverted image for the erect object. AB is the erect object. How do you get the inverted image without considering the lenses? As I told you, Gauss introduced the hypothetical planes by which the lenses need not be considered, or in other words, the refractions taking place at lenses are replaced by the principal planes and nodal planes. So, you got H1 P1, that is principal plane, the H2 P2 is another principal plane, and I have been telling you just now that there are 3 light rays which are passing from A to AH1, another light ray, another light ray takes the route AN1, the third one is passing through the first principal focus. So, AF1 K1, then from these light rays how do you get the image point A1? Okay, for the A is the point for the object. So, the image point, corresponding image point is A1. So, let us look at the light rays. A ray AH1 is drawn parallel to the principal axis touching the first principal plane at H1. As you know, H1 is the point along the first principal plane, H2 is the point along the second principal plane H2 P2, that of course you know. The conjugate ray will proceed from H2, it is a point on the second principal plane such that H2 P2 is equal to H1 P1 and will pass through the second principal focus F2. So, this is the second principal focus F2, they are the 2 conjugate points, H1 and H2 are the 2 conjugate points. So, the light ray which is incident here, conjugate point is H2. So, from H2 the light ray goes through F2 and arrives at A1. So, this is with regard to the light ray which is travelling along this direction AH1. Okay. AH1, H1 and H2 are the conjugate points. So, from H2 the light ray goes through the second principal focus F2 and arrives at the point A1. Let us look at the secondary, right. A secondary AF1 K1, obviously F1 is what? F1 is the first principal focus. So, let us look at the secondary AF1 K1, it is drawn passing through the first principal focus F1 and touching the first principal plane at K1. Let us look at the diagram again. So, the light ray is passing through the first principal focus F1 and the principal plane it meets at a point K1. Now, where are the points here? So, it is passing through F1 and it emerges at K1, right. This is the light ray I am talking about now. Okay. The light ray comes from A, passes through the first principal focus F1 and arrives at the point K1. What about K1 and K2? Similar to H1 and H2, K1 and K2 are also the conjugate points. Then from K2 the light ray should go to the point A1. So, therefore, you have here a second ray AF1 K1 is drawn passing through the first principal focus F1 and touching the first principal plane at K1. Its conjugate ray, as I told you, K1 and K2 like P1 and P2, they are the conjugate points. So, the light ray will start from K2 such that K2 P2 is equal to K1 P1. So, K2 P2 and K1 P1 will be equal. So, what K2 P2 and K1 P1 and K2 P2 should be equal, K1 P1 should be equal to K2 P2. Similarly, H1 P1 should be equal to H2 P2. That is what we told earlier. And so, now K2 P2 should be equal to K1 P1, and it will be parallel to the axis and arrive at the point A1. K1 and K2 are conjugate points. From K2, the light ray will arrive parallel to the optic axis at a point A1. So, we have been talking about two light rays. One is taking this route AH1, the another one which is traversing along the path AF1 K1, then K1 K2 are the conjugate points, then from K2 it arrives at A1. There is yet another light ray which is coming from A, that also should be considered now. That is the third ray that will be coming from the point object point A. A third ray passes through A1 T1 N1. It is drawn which is directed towards the first nodal point N1. Obviously, N1 is the N refers to the nodal point, the P is referred to the principal points. N1 refers to the first nodal point, N2 refers to the second nodal point. Similarly, P1 P2 are the first and second principal points. This may pass after refraction through N2 in a direction parallel to AN1. The third light ray takes a route along this direction. It travels from A1 to A2 N1. So, the light ray arrives at N2, and now we have here this light ray may pass after refraction through N2 in a direction parallel to AN1. The point of intersection of any of the above two refracted rays will give the image of A. The image of A for the object, you got the object point A, that the topmost point is A, and the image is obtained at A1. Let us assume the point A1 we call as let it be A1. From A1, if a perpendicular is drawn on the axis, it gives the image A1 B1 of the object AB. So, having found out the point where A will be arriving at, so A is here. For the point A, the image will be obtained at A1. So, from the point A1, draw a perpendicular to the principal axis. So, this point A1 will meet the principal axis at a point B1. So, A1 B1 is the image that is being obtained for the object that you have got AB on the principal axis. So, for the object AB which is placed at the principal axis, the image is obtained as A1 B1. Now, what we have been trying to do is, we have been looking at the light rays coming from only from the point A. From the point A, the light rays which are traversing, they arrive at A1. From the point A1, in this graphical construction, what we do is, we get the point A1. From the point A1, you draw a perpendicular to the optic axis. It meets at B1. B1 is a point on the principal axis. So, A1 B1 is the image that you are obtaining for the object that you have got AB, and this distance BF1 is equal to x1, that is the focal length. BF1 is F1 is the first principal focus, the x1 here, and similarly now, so this is the F1 here, F1 P1 is F1, and similarly we have got here like F1 P1, you have got F2 P2, right? You have got F2 here. This corresponds to the position of F2, the second principal focus. So, F1 and F2 are the focal lengths. F1 and F2 are the focal lengths. Okay. That of course, should be kept in mind, and similarly here from F2 to B1, that is x2. Similarly, from B to F1 is x1. So, B to BF1 is x1, and similarly B1 F2 is x2, and this distance F1 P1 is equal to the first focal length. Similarly, your F2 P2 is the second focal length. So, these are things that we have to keep in mind, and then finally it turns out from A1, if a perpendicular is drawn on the principal axis, it gives the image A1 B1 for the object AB. So, that is how the image is obtained for a given object kept on the principal axis using the Gaussian idea that was given, namely the so-called the introduction of cardinal points, how the image can be obtained by doing away with the successive refractions suffered by light ray because of the coaxial lens system. Because a series of lenses, you do not need about the refraction, and you use the idea of cardinal points and get the image. So far we have been talking about thin lenses and how to get the image from a graphical construction. We will now pass on to thick lenses. What do you mean by thick lens? You know, a thin lens is a lens, almost the thickness can be neglected. The lens thickness can be neglected. So, a thick lens is basically a large lens. The thickness, as I will be showing, CD that is or T, the thickness will be very large, and we will be talking about critical thickness also at a later date. So, the thick lens is basically a large lens whose spherical surfaces are separated by a large distance compared to the radii of curvatures. Hence, to obtain the image of an object, refraction of an optical system, refraction at all the surfaces ought to be taken into account. You have to consider the refraction at all the surfaces in the case of a thick lens, but by introducing cardinal points, the image can be determined directly. So, in a way similar to what we did earlier for the case of thin lenses, we introduced the cardinal points, and we will see in this lecture and in the lecture to come that the cardinal point idea can be extended to thick lenses also. So, we have again similar to the thin lens, we have the same 6 cardinal points for the thick lenses also, 2 principal points, 2 focal points and 2 nodal points. You know, in the case of thin lens, we have been talking about the principal points and nodal points, and as well as the focal points, 2 for each, that makes 6 cardinal points. So, these 6 cardinal points can be introduced for the case of thick lenses also in order to get the image for a given object. As in the earlier case, we will have the 2 cases. One is a light ray which is parallel to the optic axis being incident on the surface of a lens, and where does the light ray come to a focus. And so, similar to what we have done in the case of thin lenses, the certain same things, the first principal focal length, second principal focal length, all these things will be done here also. We will summarize this lecture, what we have seen so far. The summary goes as follows: cardinal planes or hypothetical planes, as I told you, which are introduced by Gauss to obtain the image of an object without looking at the successive refractions which are taking place at the surfaces of the 2 lenses, or a series of lenses which are found in an optical system. An optical system is containing a series of lenses. The above is a cumbersome process. By this, what I mean is the refraction taking place at each surface of a lens, the series of refractions that we studied, that is a cumbersome process. That can be done away with the idea of nodal planes and nodal points, the principal planes, and especially the cardinal point idea can be made use of to simplify the problem. So, the questions are: what are cardinal points? What are the principal planes and nodal planes? What is the essential difference between the above in ray tracing? What is the advantage of using the above planes and points? With this, we come to the end of this lecture, and the remaining things with regard to the thick lenses will be seen in the lectures to come. Thank you.